Hello everyone, I'm from the Senior Design Hyperloop team. My name is Adam Alaude, and my teammates are Tariq Karoumi, Mohammed Mekki, Khadija Mohammed, and Queen Tai. Today, we're going to talk about the Hyperloop and the linear induction motor, LIM. The Hyperloop concept was proposed by Elon Musk in 2013 as the fifth mode of high-speed transportation, consisting of passenger pods traveling at transonic speeds in a vacuum tube. Also, it is an alternative to the high-speed rail system, with a goal to cut down end-to-end travel time by 75% and reduce costs of operation, infrastructure, and maintenance. To support the concept development, the UIC Hyperloop team, along with many other teams, were founded to participate in the 2020 competition that were supposed to take place in July 2020. But unfortunately, it got canceled due to the coronavirus pandemic. As a senior design project, our team is participating in the competition by analyzing, improving, and developing a linear induction motor, LIM. Our ultimate goal from this project is to help the UIC team selecting the right design and mechanical configurations of the LIM.
Hello everyone, my name is Tariq Karoumi. I'm going to be talking about design alternatives with decision matrix. There are two main features to be considered when choosing the project alternatives for a linear induction motor: the thrust generated and the end effect. The thrust produced by a linear induction motor is a factor of the supplied voltage, the amount of slip, the size of the air gap, and the influence of end effects. End effects are caused by the relative motion between the primary and the secondary parts, generating uneven flux distribution in the air gap. This can lead to a braking effect opposing the motion. So the team has proposed three configurations to optimize the performance of the LIM. First, chamfering the teeth. Chamfering the primary teeth at the end of the LIM helps balance out the magnetic flux density and the normal force. Second, double LIM. Using a double LIM will produce higher thrust forces while eliminating attractive forces between the primary and the secondary parts. Third, alternating the distance between the motors. Changing the distance between the motor will change the interference rate between the magnetic fields. So the performance of each configuration was put under test by running finite element analysis simulations for each one of them. And the decision matrix was utilized to reduce subjectivity in decision making while clarifying and prioritizing options. A score was given based on how well the configuration meets the predetermined engineering characteristics. Chamfering the teeth and changing the distance between the motors will help reduce the end effect significantly, while using double LIM will boost the performance of propelling the pod. After all the configurations have been investigated, an improved model that has optimal performance has been derived. Based on the research and the results, the final design was selected to be a double-sided linear induction motor with chamfered teeth. This new design will help us achieve optimal performance while significantly decrease the end effect.
The LIM we have created is made of a 700 millimeter long stator with 12 teats that are 20 millimeters long and 20 millimeters apart. The separator is made out of aluminum, the primary is made out of iron, and the coils are made out of copper. The equivalent circuit of the LIM is based on the one-dimensional electromagnetic model. We analyze in detail the effect of the pole pitch, slip, and other LIM parameters. I1 is the per-phase stator current. R1 is the per-phase stator resistance. X1 is the per-phase stator slot leakage reactance. XM is the per-phase magnetizing reactance. R2 is the per-phase rotor resistance, and I2 is the rotor phase current. Here are the results for the equivalent circuit. And here are the results for the LIM design parameters. One of the variables that is tied to the end effect is the number of poles. There is an indirect relationship between the number of poles and the end effects. As you increase the poles, there is a decrease in the end effect phenomena. Also, the poles can only be even numbers, which is why we chose 4. Likewise, the slip was set to be at 5%. We chose to keep the slip low to improve the performance of the LIM, as a higher value will decrease the overall efficiency of the system.
The final design of the double-layer linear induction motor is made of one aluminum separator, two iron primary. Each primary has 12 slots. There are 24 coils that wrap around these slots. From the figure, the coils are represented by three colors, red, yellow, and blue, to represent three phases of current. Each phase is offset by 120 degrees. After running Ansys and electromagnetic simulation, the magnetic flux density generated by the LIM had the maximum value of 0.5 Tesla. The maximum magnetic field intensity is 4.5 to the power of 5 amp per meter. More of the magnetic flux density and magnetic field intensity point to the left. Because of the N effect, a small amount of magnetic flux density and magnetic field intensity point to the opposite direction. The LIM applied a force of 0.452 Newton in the x direction on the separator to put it to the left, or in other words, the separator applied a force of 0.452 Newton on the LIM to push it to the right, the direction of moving. The force applied on the separator includes 0.009 Newton in the y direction and 0.005 Newton in the z direction. Compared to the force in the x direction, there is barely any force in the y and z direction. All the LIM stay balanced in the y and z direction. That means it will keep stay on track while moving forward.
After conducting the feasibility study and interviewing the UTC director, the team has concluded that Hyperloop surpasses any other mode of mass transportation in terms of time travel, frequency, energy consumption, and the cost to user. Hyperloop offers an innovative mode of transportation which is futuristic as well as cost benefits, both to the user and to the state or corporation that chooses to incorporate Hyperloop into their city's transportation modes. As many financial benefits as Hyperloop offers, there are non-financial benefits that are offered to the city or state that chooses to build a Hyperloop pod in their city. Non-financial benefits include decongestion of traffic on roads, which translates to drivers arriving at their destinations quicker without being frustrated from traffic. Another non-financial benefit includes the cost of emission saving. Over a number of years, a reduction in emission would greatly benefit the quality of life in an urban city. Another benefit to decongestion is less wear and tear on roads, which would reduce the maintenance cost. Our senior design team has identified a couple of factors which impact the creation of Hyperloop. One factor includes the price of land. Another factor includes the ease of access to laborers. Since Hyperloop can navigate in a curve, there wouldn't be a requirement to dig tunnels underground or underwater. The capital cost of building might be high, but not higher than maglev trains, high-speed rail, or the cost required to build an airport, and planes. However, the reduction in energy consumption costs and the frequency of trips that Hyperloop will be able to provide would eventually prove that Hyperloop is a better mode of transportation than plane, maglev train, and high-speed rail transportation. Another point the team would like to highlight is that airlines actually lose money from short trips between states, and they break even or make profit from long trips. Providing a mode of transportation such as a Hyperloop between states would prove to be profitable, less time-consuming, and less carbon-emitting mode of transportation. As shown in the first slide of the feasibility study, the speed of Hyperloop surpasses any other mode of transportation, and due to its non-existent security screening, Hyperloop time travel would be reduced to 26 minutes at minimum to 35 minutes, and that's just an approximation. Given the high speeds of Hyperloop, it would be able to perform more trips per hour than planes, maglev trains, and high-speed rail. Also, due to Hyperloop's high speed, it might be potentially noisy and might cause people with motion sickness a difficult time. However, it would provide more leg space than plane transportation. As previously mentioned, the energy consumption of Hyperloop is much lower than any other mode of transportation, mainly due to its levitation magnets and LIM, which drastically reduces friction. Also, the power source will mostly come from solar cells. The user costs shown in this last slide aren't concrete and have been taken from Hyperloop Alpha's interviews and announcements. However, due to its very low energy consumption and very high speeds, there is no reason for Hyperloop to charge more than plane trips or high-speed rail trips, unless solely done for profit.
In conclusion, each design has a unique feature that will minimize the end effects experienced at speeds over 200 miles per hour. Rather than choose one feature that supersedes the others, it was determined combining the features will yield better performance. Thus, it was decided that a double LIM with chamfered teeth is the best solution. This is because a double LIM will increase the thrust of the pod, and the chamfered teeth will balance out the magnetic flux density and the normal force. Both features will minimize the end effect experience over 200 miles per hour. Initial testing using Simulink and Ansys AIM have supported the expected results. For future work, the third design variation, widening the distance between the motors, can be incorporated into the current model to see if this feature will improve the LIM's performance. We would like to thank our advisor, Professor Atif Yardemsi, for guiding us through this project, as well as the engineering design team at UIC.